right, guys, this is our last section. We're going to skip 8.6 and we're going to do 8.5. I don't think we're going to get all the way through it, but I'll at least talk to you about kind of what we're going to miss, but at least relate it. Okay, actually, we can do it right away. Here we go. We're going to talk about the Maclaurin series, okay, the Maclaurin series. We're not going to get to the Taylor series, but I'll try to at least reference it so that you kind of at least know they're very similar. So we're going to focus on the Maclaurin series. Okay, this is kind of cool. We know sine, right? We know a sine. You can write sine as a power series. We can write sine as a power series. Here you can even see it a little bit more. All of this is your C sub n, and here is your x sub n. We're going to be able to write it as a power series. Either way, sometimes they write it like this, but here you can see the C, the coefficient, and then there's your x to your n. There's a little bit more to it, and we're going to talk about how come it's not just x to the n in a few minutes. Okay. All right, so let's evaluate this, though. Let's evaluate sine of x. So what that means is we're going to plug in a 0 every place there's an n, and we're going to come up with a value. So if we plug in a 0, anything to the 0 power is 1, right? So that guy's 1. Make sure I have enough room. Let's see. And then if we plug in a 0 here, we get 1 factorial. And then if we plug in a 0 here, we just have x to the first. Okay. Plus, because it's a summation, now we're going to plug in a 1. Well, now when we plug in a 1, we actually get negative 1. When we plug in a 1, we get 3 factorial. And then when we plug in a 1, we get x to the third. Okay. And then plus, so that was 0, 1. Okay, let's plug in a 2. When we plug in a 2, negative 1 squared becomes positive. We plug in a 2, we get 5 factorial, right? 2 times 2 is 4, plus 1 is 5. And then same thing here, right? When we plug in a 2, we get x to the fifth. Okay. Let's see. Where are we at? 0, 1, 2. Let's plug in a 3. When we plug in a 3, technically it's plus because it's a summation, but when we plug in a 3, that's negative. When we plug in a 3, we get 7 factorial, and then x to the 7th, and then plus dot, 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 right? It keeps going on. Okay, so let's clean this up just a little, because usually we see this. You're going to see sine of x. We're going to shrink it down or just make it a little bit more efficient. Actually, we could just do x, right? I was going to do x over 1, but let's actually even change this to just x, because we're going to write it probably the way you'll see it the most. So all of this goes down to x, right? Because 1 factorial is just 1. The rest of these will stay. So this will be what we'll do here to clean this up is we'll do negative x to the third over 3 factorial plus x to the fifth over 5 factorial minus x to the 7th over 7 factorial plus dot, dot, dot. Okay. Now, what I'm saying is sine of x, all right, and we're going to do some examples here, is sine of pi over 3. We can actually plug pi over 3 into this and get the same answer as if we evaluated sine of pi over 3. So this one, we know the exact value. Think of your unit circle. What is the value of pi over 3? Okay, so pi over 3 is up here. Cosine short long, square root of 3 over 2. Okay, all right. What would, and I don't know, let's see, I want to, hopefully you can see this. What would the calculator give us? So if I do sine of, what was it, pi over 3? Pi divided by 3, I get 0.866. Let's take it out a few places. Let's do 0, 2, 5, 4, okay? Now, what is the square root of 3 divided by 2? Because I thought sine of pi over 3 was square root of 3 over 2. Calculator is saying it's this 0.866. So square root of 3, if I can do this here, square root of 3 divided by 2, hopefully we know the answer already, is this exact same thing. So these two are equal. We know that. We've memorized this one, but we know that the calculator can give us pretty much anything. Hopefully it'll, I know, I will not miss this camera zooming in and out. That's one thing for sure. Okay, so what does the power series say? The power series says that I can come up with an answer for sine if I just take x, let's even go to this one, if I just take x and plug it into there. So I'm going to do, plug it in here, pi over 3 minus pi over 3 cubed over 3 factorial plus pi over 3 to the 5th 5 factorial minus pi over 3 to the 7th over 7 factorial. Now technically I'm supposed to go on. I'm supposed to keep going because technically I'm saying it's the entire series. But you're going to see that you only need to take it out a few terms and you're going to get the same answer. Okay, so what I did is, let me clear this. I'm going to do second enter. I already started the process. Oops. Okay, so there it is. Oh, you guys can see that's an issue. Okay, so here's my x minus x to the 3rd divided by 3 factorial plus x to the 5th divided by 5 factorial. So then it's minus x to the 7th and then divided by, and if you go to math, and you're actually not going to have to do this, so don't panic, but you will not have to do this. If you go to math and then over to problem, 4 is the factorial. Okay, but you're not actually going to have to do this. I'm just showing you how this kind of all works. Oops, I forgot to put in 7. 7, so we get to do it again. 7, math, problem, factorial. Okay. All right. Now, when I hit enter, we're not going to get the right answer because I have something. I don't think so. Okay, no. Okay, so now what I want to do is I want pi over 3 in for x. So I'm going to do pi divided by 3, and I'm going to store it for x. Okay, so pi over 3 stored for x. Okay, then I'm going to do second enter. Then I just call up. So now the calculator is going to take pi over 3 and plug it in everywhere I have an x. I did some second enters. That'll call up, keep calling the stuff up. And look what I get. We could have done it by hand, but this is a little bit quicker. We get oops, it's gone again, isn't it? 0.8660. We get 2127. So at some point it is a little bit different, but to 5 places, can you see that? To 5 places, it is accurate. That's pretty cool. We can write sine as a polynomial. We can write sine. Technically, it's an infinite polynomial, and technically it keeps going on. But just with these four terms, we can get right to 5 places. That's pretty cool. And that's a whole goal. Take functions that are maybe hard to work with, or maybe hard to work with in certain situations, and you can change it to a polynomial. That's the goal of the Maclaurin series or the Taylor series. Take a function that could be hard to work with or is maybe hard to work with in a certain situation, change it to a polynomial. That's pretty cool. Okay, so here we used a finite number of terms. Remember, technically this goes on forever. So we actually only used a finite number of terms. We only used 4 terms, right? We only used, let's see, where were we? 1, 2, 3, 4. So we only used 4 terms, okay, to estimate this power series. It was a great estimation because this is one where we already know the answer. And with these 4 terms, we already had a good estimation, okay? So let's just say we use a finite number of terms to estimate the power series answer, okay? So the expression we used was called technically, because we only went out 4 terms and actually stopped, we actually stopped, right? If it keeps going on, it's the series. If we say, hey, we're only literally going to use 4 terms, then we can actually call it a polynomial. So we actually did a Maclaurin polynomial because we actually stopped, we got this number with literally just 4 terms. Okay, this would be called, because my highest exponent, because I stopped here, my highest exponent was a 7th, this would actually be a 7th degree Maclaurin polynomial. Okay, so just to know the difference between a polynomial and a series. A polynomial is when you finally take the series and you say, hey, I'm just going to stop here. This is plenty, this is enough. Then we can actually call it a Maclaurin polynomial. Okay, but this is cool. This is changing a function into a polynomial. Okay, all right. Let's see, where else do we want to go? Okay, there's much more. Oh, this was just, I don't know, I don't think we have to do all these, but this was just to show you like a different variation. Because, okay, it was kind of cool, but, you know, we already knew the sign of pi over 3. But this is what happens if there is no pi. This is still an angle measure, all right? This is still an angle measure. The angle measure is just something we're not familiar with, 0.7, okay? So this is still this angle measure, but it's definitely one that we don't have memorized. So we don't ever think of this as an exact value, okay? But we can get it from our calculator. Let's at least do one. We can get it from our calculator, sine of 0.7, okay, gives us 0.6442. Or we can now use the Maclaurin. So the Maclaurin, this one we could maybe even do in our calculator. So maybe let's at least do this one. The Maclaurin says we're going to do 0.7 minus 0.7 to the 3 divided by 3 plus 0.7 to the 5th, divided by 3 factorial, sorry. 0.7 to the 5th divided by 5 factorial, and then minus 0.7 to the 7th divided by 7 factorial. Ooh, look out. And we're really, I mean, technically it goes on, but we're just going to use those 4 terms. Okay, so we're going to kind of change it to a polynomial. Yeah, so you can even do that with your calculator if you want. Or what I could do here is I could now do 0.7 store 4x. Okay, and then I do second enter, and I keep doing second enter until I have that polynomial that I liked. There it is. Second enter brings that up. So now it's going to take 0.7 and put it in for all my x's. So it's literally going to do this for me. And there it is, 0.6442. Okay. In fact, some people say that this is how the calculator actually calculates sine of 0.0. There is some on the internet, of course, right, that say that is not true, and there's other programs that they use. But I don't know, maybe it was once used, and that's kind of like a situation where I can't do 0.7, but I can use this polynomial. Okay, so one theory is that's what the calculator, maybe at one time it was, and now they have other programs and different things. But yeah, that's kind of cool that we can actually use this polynomial to evaluate something like trig. And this was the same thing. I don't think we have to do this. Same thing here, pi over 12. It has a pi in it, but it's not one that we have memorized. So again, the exact value we wouldn't know. We can grab the calculator, or now we can do the Maclaurin series. Same thing with this. Don't let this throw you. It's not when is sine 1. That's not this. This is an angle measure of 1. Okay, that's an angle measure of 1 radian. This is radians, not an x or y value. Okay, all right, but you get the idea. I think we get the idea that we can evaluate trig or other functions using these Maclaurin series. Now, the goal of today is that we write these on our own. That's the goal. So I wanted you to kind of see what we're doing here. We're coming up with sigma. We're coming up with a series in notation. We're going to write this for the given trig function, or not for any function, not necessarily trig. Okay, and to do that, you actually kind of start out backwards. So we're going to do something like this, and then kind of work our way up this way. Okay. All right, so those two done. Let's keep that handy though. Oh, one other thing. Let's see, before we get to our examples. Okay. one thing I said, we're not really going to get to the Taylor series, but I wanted you to understand that the Maclaurin series we know is when A equals 0, okay? And so really the Maclaurin series gives a good estimate with only a few terms, right? We just saw that, but it has to be when X is close to 0, okay? It can work, but it can work. It might not even work. But if it does work, you got to take it out a lot of places, okay? We're talking like hundreds of places. So what do you do if you got a number like here? This X value, this is my X value, nowhere close to 0. That's not considered, oh, please go back to, there we go. This is not close to 0. So my X is 15. That's when you do a Taylor series. So if we're not close to 0, then you would do a Taylor series. Let's see if there's anything else. Okay, so let's write not close to 0. Not close to 0. Okay. And so you want to choose an A. Choose an A close to 15. But you do have to, and we're not going to get into it, but you do have to be able to work with it. Okay, so if we're dealing with trig, what has to be in it if we're going to work with it? Pi, right? We know stuff with pi. What happens if we choose A to be 5 pi? It's 1, and again, don't panic. I'm just explaining things. We're not going to have to do this. But all the way around is 2, all the way around is 4, and then here is 5. This is a value we know. We know sine of 5 pi. Okay. So my A, I would choose 5 pi. What's 5 times pi? What's 5 times pi? 5. We know it's right around 15, right? Because pi roughly is 3. Let's clear this out. Let's do that. So 5 times pi gives us 15.7. Okay, but I would actually leave it as 5 pi when I'm working with it, because I would have to do something with trig. But as long as you know that you would, what was I going to write? This is something like 15.7. So I chose something that I can work with, 5 pi, and it's around my X value. So you make A something you can work with depending on the situation, but it has to be close. All right. So the Maclaurin series is 0. So if you're going to write a Maclaurin series, it really only works when your X value is close to 0. Okay. What do we do if the X value is not close to 0? This is when then we go to the Taylor series. Okay. Because we can then center it closer to the X value. Okay. All right. So let's look here. This is our pattern. A Taylor series. Here's our A values, okay? And here, this is what we're going to be doing today. Here's our Maclaurin series. We're going to be writing one of these. Notice my A is 0, because a Maclaurin series, A is always 0. And then I don't have this. If my A is 0, this is gone. And so I just have X to the n. Okay. All right, so this is n factorial. This is X to the n. I always kind of go backwards. Okay, this is easy to do. This is easier to do. What is this say? This is like if I have a first derivative, second derivative, third derivatives. These are derivatives. Okay, so we have to come up with a whole bunch of derivatives. When n is 0, that's my original function. When n is 1, that's my first derivative. When n is 2, that's my second derivative. When n is 3, third derivative, and we get the point, right? Okay, so in order to write this, we're going to need to figure out derivatives. All right, who would have thought? Okay, so we did all that. Let's see. Trying to keep some order, and I probably completely failed. Okay, I think we're doing okay though. All right. Okay, so how do we write these? Remember our goal, I think this is a different piece of paper, but our goal is to write one of these all on our own. Okay, so here are the steps. We're done with that. How are we doing on time? Okay, we're doing good. We're doing good, guys. Okay, so how to write a Maclaurin series or, a Taylor series, we can just adjust step 2. So we have to find the first few derivatives. Sometimes 4, maybe 6. We'll see. I would say probably not more than 6. Once you see a pattern too, then you can always just kind of fill in the rest. I'll show you what I mean by that. Evaluate each derivative using A. So remember I said for the Taylor series, I had to have an A value that I could work with. So for trig, I needed an A value that I actually knew. Now for Maclaurin series, it's always 0. Okay, so we're going to evaluate each derivative with 0. Okay, so remember, we're going to do Maclaurin, so we're going to evaluate each derivative with 0. Okay, all right, and then we write out the terms. Okay, and then when we write out the terms, remember I said we kind of go backwards. We're going to write out these terms, and then from this, we're going to have to correlate to this. Okay. All right, so write out the terms using values from step 2, and then if possible, express the series using that sigma notation. Okay, those are our steps. Okay, all right, so why is this all messed up? Okay, so that is that. Oh, here. Okay, so we did that. Okay. We know the answer. We know the answer to this. But this is what our homework is going to be. Okay, we got 4 problems that we're going to, yeah, let's do this. This is what our homework is going to be. Let's practice. We know what the answer is going to be. We know that we should get that sigma notation. Let me see if I can find it. I told myself I was going to be organized. We want to write this. We're going to write this. Okay, so the good thing is we know the answer. Let's see if our process works. Okay, so the first thing we're going to do is find the first few derivatives. Okay, so f of x is equal to sine. We need that guy. Okay, what is the first derivative? The first derivative, let me get rid of this, just to see if that'll help focus. All right, so the first derivative of sine is cosine, right? Okay. Put this here. All right, second derivative. Derivative of cosine is negative sine. Okay, and you can do this too. You can actually write a number. Usually after 3, we write a number. Oh my goodness, what are you doing? Don't fail me now. Okay. Usually after 3 for sure we write a number. If you guys want to just write numbers right away, just this kind of is more familiar, right? We know that that's it. To remember that we're taking derivatives. All right, now what this is a little crazy, right? The derivative of sine is cosine. My coefficient has to come down. So this negative is just coming down. My derivative of sine is cosine. Okay. F of 4. We would definitely at this point write a 4. Technically, I think it's supposed to be in parentheses, but let's not make it any more messier. Okay, so now the derivative of cosine is negative sine. But because I have this extra negative, right, it would be like negative, but then it would be negative sine. So we can just write that then as positive sine. My derivative of cosine is negative sine, but I have that extra negative there. Okay, and let's at least go out one more. The 5th derivative. Some of these you don't have to go quite as much with trig. It's a little bit harder, of course, right? Trig is always harder. All right, the derivative of sine is cosine. Okay. Okay, so now, let me see. Does it help if I tighten this? Oh, guys. Okay, I will not miss this at all. Okay, now, where is my paper? Okay, so step 1, done. Find the first few derivative. Now we're going to evaluate each derivative. We're going to put in a 0, okay, because we're doing Maclaurin, we're going to put in a 0. So we're going to evaluate each of these with a 0. So we're going to do f of 0, which means we're going to do sine of 0. And what is sine of 0? You could, do I have to write it bigger? Can we see? All right. Sine of 0 is right here, right? 1, 0. Okay, so this, remember, x is cosine, y is sine. So sine of 0 is 0. Okay, the first derivative evaluated at 0 is cosine of 0. Cosine at 0 radians is 1. Okay, second derivative, we got to plug in a 0. So negative, make sure you reference back here, negative sine of 0. Well, that whole thing is 0, right? All right, because this is 0, we don't care about the negative. All right, f of, we could do third derivative or we could put a 3, either one. This literally means we're taking a 0 and plugging it in here. We're finding the third derivative and plugging in a 0. So negative cosine of 0. All right, cosine of 0 is 1, so this equals negative 1. All right, 4. Okay, so we take the fourth derivative, we plug in a 0 for the fourth derivative, so we're doing sine of 0, which equals 0. All right, and then we're doing the fifth derivative, and we're going to plug in a 0. We're going to put in a 0, so that is cosine of 0, which equals 1. Okay. All right, so step 2, evaluate each of the derivatives, plugging in a, which is our 0. Okay, now we're going to write out the terms. So we are going to, okay, we're going to use this guy. Okay, so we're going to now write out the terms, n equals 0 to infinity. This means all these derivatives evaluated at 0. So that's that right there. N to the z, or n factorial, x to the n. Okay, so we're going to plug those in, and we're going to write out our terms. Okay. I'll keep that guy handy. Okay, so what happens when we plug in a 0? Well, when we plug in a 0, we're doing the original function evaluated at 0. The original function evaluated at 0 was 0. Over 0 factorial, x to the 0. Okay. Plus, now we're going to do 1. So f with a little 1 here, evaluated at 0. So that means the first derivative evaluated at 0. First derivative evaluated at 0 is 1. Over 1 factorial, x to the 1. Plus, let's see, so we did, let me see. So this was when, this, well, we could just keep going. This is when n was 0, right? This is when n is 1. So what is it when n is 2, right? So we plug in a 2. So we want f with a little 2 evaluated at 0. That means the second derivative evaluated at 0 is 0. Over 2 factorial x squared. Okay, plus, now when n is 3, okay, so that means f with a little 3, here you can visually see it, right? Evaluated at 0. So that's the third derivative evaluated at 0. That's negative 1 over 3 factorial x to the third. Okay. All right, so then we go n is 4. N is 4, so that means we're looking for f, the function, the fourth derivative evaluated at 0. The function, the fourth derivative evaluated at 0, 0 over 4 factorial, because now we're just doing n, and we plug it in n there, x to the n. All right, and then one more, at least one more that we have written. Okay, if we need more, I think we'll be able to see the pattern as well. All right, the function, the fifth derivative of the function, because we're plugging in a 5 for n, evaluated at 0. That's this guy, 1, 5 factorial, x to the fifth. Okay, now sine's a little bit harder. I'm kind of glad we know the answer at least, because some terms actually drop out. I think randomly on the last section I told you this, but 0 factorial is 1 by definition. Okay, 1 factorial is 1, 2 factorial is 2 times 1. I did this too. I don't know if I hope you guys know what factorial is, but maybe not. Here's a list, and here's where I got it. So like 4 factorial is 24, and you get it by doing 4 times 3 times 2, technically times 1, but that doesn't really make a difference, right? And here, 0 factorial is 1 by definition. 1 factorial then is technically times 1. 2 factorial is 2 times 1. Again, you know, the 1 is optional. Obviously, we know that 6 factorial is 720. There may be a few cases, I'll reference this in the last problem, where if you see these numbers, you have to think factorial. But I'll try to show you another way. But it might be nice to have this list anyways in case you see these numbers pop up. And you're only going to see 1 or 2 of them. All right, so that was a side note on factorials. Okay. All right, so where were we? Okay, so this guy here, 0 divided by technically 1 is 0, so this whole term drops out. Okay, this guy is good to go. This, let's just leave it. We're going to leave it like this. Because remember, this is the hardest part. We have to come up with a pattern. 0 divided by anything is 0, so this guy is gone. This one, we actually have a -1, 3 factorial x to the 3rd. Okay, this is gone because it's 0. Do we see why? This is a 0, so 0 divided by anything, the whole thing is 0, right? And then the next one is 1 over 5 factorial x to the 5th. Here's what I said. If we need a few terms, oh, wait a minute. Oh, okay, no, we're okay. Let me slide it up a little. Okay. If we need a few terms, I'll write it in orange maybe because I'm just kind of making this assumption. But do we see how, now be careful, do we see how this goes plus, minus, plus? So the next one would be, and again, this is only if you need it. You don't have to do this, but it would be -1, 7 factorial x to the 7th. And if we needed one more, it would now be, it alternates, so this would be +1, 9 factorial x to the 9th. Okay, because those even ones are going to be 0 and they're going to drop out. Okay, if you're not sure, then you would have to do more just to be sure, but I think you can kind of start to see the pattern. Okay, guys, we're almost there. We now want to write, this in sigma notation. So now normally we can just go here. This is a little harder because these are dropping out. So we're going to take a second look. What happens here when n is 0, when n is 1, when n is 2, when n is 3, and when n is 4. Okay. So most of the time we can just reference this exactly. Remember the trig one didn't have an n here, and this is why. Because these terms drop out, we're going to now try to get rid of those and still write a pattern. Okay. So, and that's why sometimes I like to write more, because I think it's easier to see stuff here. Okay, do you see how 4 times 2 is 8, and then it's 1 more? 3 times 2 is 6, 1 more. 2 times 2 is 4, 1 more. Okay, so the bottom is going to be 2 times n, and then we have to add, and then we have to add 1 more, okay? And we have to do the factorial, okay? This is a sigma, n equals 0 to infinity, okay? Oh, I know what did I want to, all right, how are we doing? Hopefully I didn't go too far. Oh, no. All right, let's keep going. Okay, this same thing, right? If that's how we got the 9, so this is x to the 2n plus 1. Okay, and then notice our tops are always 1. The only thing is they alternate. So it's -1, but when it's even, then it becomes positive. When it's odd, it stays negative. When it's even, it's positive. So I can just put an n up there, because then when it's even, the negative's going to be positive. And when it's odd, then it will be negative. And here is one of the very first things we saw. That's what, let me see if I can find it. Here it is. I think I found it. All right. It is this guy, right? Negative, let's see, can you guys see that? -1 to the n, 2n plus 1, There it is. That's our goal. Our goal is to take a function and write it as basically an infinite polynomial. Okay, because sometimes I know this looks crazy, but believe it or not, sometimes these polynomials are a lot easier to work with. This looks pretty crazy, but remember, this produces this, and that's not too bad. Okay, this looks, I think, more intimidating. This produces this, which is sometimes easier to work with than the given function. Okay. All right, now it's not. Oh dear, it's not quite that easy. We have to, there's one more piece to this. Okay. And then we got to go to examples. Oh my goodness. Oh, too bad we can't do math all day, right? Okay, so here's the last piece to this puzzle. If we're writing a power series, okay, Maclaurin and Taylor series are power series. They converge, but not all the time, right? So we have to test to see when this converges, okay? So for what x values will this power series actually be, can we actually evaluate it, okay? Remember, a power series always converges, but you have to check for the x values. How do we do that? To find the radius of conversion, we use the ratio test. Notice they're going to ask us for the radius of conversion. We don't have to give the interval, okay? The interval's easy except for what? The interval's easy except for the endpoints equal 1, and so we would have to do 2 more tests. Remember from last section, you have to test then the endpoints. So our book is actually kind of nice. We just have to state the radius. So we don't have to do the extra 2 tests for the endpoints, okay? All right, so let's take a look at this. Let's test, let me put it here. Actually, let me rewrite it, huh? We want to see when this power series converges, okay? And the easiest way to do that, x to the 2n plus 1. The easiest way, it gets a little messy, but the easiest way to do that is the ratio test. So the limit, we had to do limit in our last section, right? The limit as n approaches infinity, absolute value. Now we had to do n plus 1, negative 1, n plus 1, over, now just be careful here, it's 2n plus 1, but then you've got this plus 1 right here is here, factorial. And then you've got same thing here. You've got 2, and then you got n plus 1, and then you got that extra plus 1. Okay. And then we got to keep going, right? Because then we put that over this. So we've got negative 1 to the n. This time I'll put this in just in the numerator, 2n plus 1 divided by 2n plus 1 factorial. Okay. So let's clean this up. Limit as n approaches infinity. We're going to rewrite the top one. Oh, remember, we're going to rewrite this as negative 1 to the n times negative 1. This one is this exponent right there. Let's put this guy, let's see if I have a different pen. So this is 2n plus 2. I have to distribute, but then I still have that plus 1. So this is going to be 2n plus 3. Okay, just want to make sure that looks okay. All right, x to the, so this, let me write it like this. This is 2n plus 3. So I have x to the 2n, and then I have x to the third. Okay, all over. This guy here's the same thing, the same exact thing here. So it would be 2n plus 2 and then plus 1, so plus 3 factorial. Okay, times, and then let's flip this guy over. So this guy would be 2n plus 1 factorial, because instead of dividing, let's bring this all the way down. Instead of dividing, we're going to multiply by the reciprocal. And then this guy will be negative 1 to the n. And then this would actually be what? X to the 2n, and then x to the first. Okay. So now what cancels out? These guys cancel out. Okay, x to the 2n cancels out. This negative 1, but we're taking the absolute value, so sometimes I write ABS by it. So that goes out because of ABS. Okay, how is this going to cancel? 3 x's on top, 1 x on the bottom. Let's see, does my orange show? Yeah, good enough for this. Equals the limit. Okay, where are we? So that goes out. We're going to cancel this to an x squared. Okay, and then how does, maybe I'll do it in blue. How does this cancel with this? Okay, the blue's not writing very well. Maybe I'll do brown. So this is +1, this is +3. So my up to my 2n plus 1s would cancel. So I still have 2n plus 2, and I have 2n plus 3. Okay, so this goes away completely. That cancels with that, except I've got these last 2 terms left. So this is 2n plus 2 and 2n plus 3. Okay, and I think everything else cancels. I think we're in good shape. Okay, so now remember, I'm doing the limit as n approaches infinity. So these n's, just these n's, are getting bigger and bigger and bigger. So those are headed towards 0. So what I really have is 0 times the absolute value of x squared, and the ratio test, maybe I'll switch back to this, the ratio test says it has to be less than 1. Well, no matter what you give me, if x is 7, 7 squared is 49, but I have to take it times 0, which would be 0, which is less than 1. All right, if x is 4, 4 squared is 16, I take the absolute value, but then I take it times 0, it's going to be less than 1. Okay, because no matter what I put in for x, my answer over here is going to be 0, which is going to be less than 1. So the radius is infinity. So that just means that I can pick any number I want for x, and everything's going to work out great. Okay. All right. So we're going to stop there, and then we're going to get 2 examples. Okay.